Bismillahirrahmanirrahim. Assalamualaikum, brothers and sisters. Today's episode focuses on the concept of angular quantum number as applied to rotational spectra of a diatomic molecule such as a silicon monoxide molecule. For more details, stick around till the end of this video. Watch and learn. The problem is the most common silicon atom is 4.646 times 10 raised to the negative 26 kilogram, and the mass of the most common oxygen atom is 2.656 times 10 raised to the negative 26 kilogram. When a molecule of silicon monoxide makes a transition between the angular quantum number L equals 1 and L equals 0 rotational levels, it emits a photon of wavelength 6.882 millimeters. Find letter A, the moment of inertia of the silicon monoxide molecule. Letter B, the reduced mass of the silicon monoxide molecule. And letter C, the distance between the silicon and oxygen nuclei. Our discussion focuses on the fact that molecules have quantized energies determined by their rotational and vibrational states. But you see, in this episode, we only focus on rotational levels, more commonly known as the angular quantum number L, associated to a diatomic molecules like silicon monoxide. And as illustrated in figure 1, we model a diatomic molecule as a rigid dumbbell or 2-point masses M1 and M2 separated by a constant distance or not that can rotate about axis through its center of mass perpendicular to the line joining them. What are the energy levels associated to this rotational motion? We know that when a rigid body rotates with an angular speed omega about a perpendicular axis through its center of mass, the magnitude L of its angular momentum is given as L equals the product of I and omega, where I is the moment of inertia of the body. Its kinetic energy is given as one half of the product of the moment of inertia and the square of the angular speed, or K equals one half I times omega squared. So when we combine these two equations, we get the kinetic energy being equal to L squared divided by 2 times I. And since there is no potential energy, the kinetic energy, capital K, is equal to the mechanical energy denoted by capital E, being equal to L squared divided by 2I. And the fact that angular momentum is considered to be quantized, we can express the angular momentum as capital L equals the square root of the angular quantum number small letter L times quantity small letter L plus 1 and multiplied by a constant known as Planck's constant divided by 2 pi, where the angular quantum number small letter L can either be 0, 1, 2, and so on. In other words, transitions between rotational states that involve photon emission or absorption are allowed only if the rotational level, right, E sub L changes by 1, right? The constant h bar here is Planck's constant divided by 2 pi. So again, when you combine the two equations for energy, capital E, and angular momentum, capital L, we obtained the equation for the rotational energy levels, capital E sub L, equal to the angular quantum number, small l, times quantity L plus 1, and then multiplied by h bar squared divided by twice the moment of inertia, capital I. And as shown in figure 2, we have the ground level or small letter L equals 0. And the first 4 excited rotational energy levels for a typical diatomic molecule. Notice that the levels are not equally spaced. So, going back to our given problem, we have here the mass of uh, the silicon atom, the most common silicon atom. Okay, we denote that by M1 equal to 4.646 times 10 raised to the negative 26 kilogram, while the mass of the most common oxygen atom, which we denote as M2, equals 2.656 times 10 raised to the negative 26 kilogram. When a molecule of silicon monoxide makes a transition between the angular quantum numbers small l equals 1 and small l equals 0 rotational levels, it emits photon of wavelength lambda, given here as equal to 6.882 millimeters, or when converted to meter, that's 6.882 times 10 raised to the negative 3 meters. Our target variables, we have in part A, the moment of inertia of silicon monoxide molecule, right? That's denoted by capital I. And in part B, the reduced mass of the molecule denoted by small m sub r. And lastly, in part C, the distance between the what we call silicon and oxygen nuclei. We denote that as R sub naught. Before we can find the moment of inertia of the silicon monoxide molecule, we first have to compute the photon energy, capital E, using equation number 1, which says that the photon energy, capital E, is equal to the product of Planck's constant, small letter h, times the speed of light in vacuum, and then divided by the photon wavelength lambda. That is, the photon energy, capital E, is equal to 6.626 times 10 raised to the negative 34 joules second times 3.000, okay, times 10 raised to the 8th power meters per second. That's the value of the speed of light in vacuum, and then divided by the given photon wavelength, 6.882 times 10 raised to the negative 3 meters. So when you do our math, we get the value or the amount of the photon energy, capital E, equal to 2.888 times 10 raised to the negative 23 joules in 4 significant figures. The photon energy, capital E, that we computed earlier is equivalent to the energy emitted when a molecule of silicon monoxide makes a transition from the rotational level small l equals 1 to small l equals 0, right? And this energy expressed in equation 2 is directly proportional to the angular quantum number small letter l, right? Also known as the rotational level, but is inversely proportional to the moment of inertia, right? Capital I of the molecule, right? Uh, the moment of inertia is for an axis through the molecule's center of mass, that is. So, from this equation, we can compute the moment of inertia, capital I, right, that is required in question letter A, right, for a diatomic molecule with axis through the molecule's center of mass. Or, that is, the moment of inertia, capital I, is equal to the rotational level, small letter l, times quantity, small letter l plus 1, and multiplied by the square of h bar, or Planck's constant, divided by 2 pi. And then the whole thing will be divided by twice, okay, the amount of the energy, capital E sub L, or the photon energy that we have already computed earlier. All right. So to determine the value of h bar, we have h bar being equal to Planck's constant, small letter h, divided by 2 pi. Okay, and taking the SI value of the Planck's constant, 6.626 times 10 raised to the negative 34 joules second, all right, we obtain the value of h bar, right, equal to 1.055 times 10 raised to the negative 34 joules second, right? And in determining the moment of inertia capital I, that has to be squared, all right? H bar has to be squared, and then, of course, multiplied by small l times quantity small l plus 1, then divided by twice the value of uh, the energy, right? Uh, 2.888 times 10 raised to the negative 23 joules, right? So, when we do our math, we have the moment of inertia, capital I equals small l times quantity small l plus 1, the square of the h bar, okay, equal to 1.113 times 10 raised to the negative 68, right? Joules squared, second squared, and then divided by twice the product of, twice the value of the energy, 2.888 times 10 to the negative 22 joules, when multiplied by 2, will give us 5.776 times 10 raised to the negative 23 joules, which, of course, can be simplified further as small l times quantity small l plus 1 multiplied by 1.927 times 10 raised to the negative 46 kilogram meter squared. So, for rotational level small l equals 0, the energy capital E is also equal to 0. And the moment of inertia capital I is equal to 0 as well. So, for small letter l equals 1, we need to compute the value of the moment of inertia capital I. That is, capital I, our moment of inertia, equals small letter l times quantity small letter r plus 1 multiplied by 1.927 times 10 raised to the negative 46 kilogram meter squared. And that simplifies to capital I, or moment of inertia, equals 1 times 2 and times 1.927 times 10 raised to the negative 46 kilogram meter squared, which of course will result to the amount of moment of inertia, capital I, okay, when the angular quantum number small letter l is equal to 1. So the moment of inertia equals 3.852 times 10 raised to the negative 46 kilogram meter squared, rounded to 4 significant figures. In part B, we are to determine the reduced mass of the molecule uh, silicon monoxide. So we use equation number 3, okay, where the reduced mass m sub r is equal to the product of the two masses, m1 times m2, and then divided by the sum of the two masses, m1 plus m2. Right? So substituting the quantities, we have the reduced mass m sub r equal to 4.646 times 10 to the negative 26 kilogram times 2.656 times 10 to the negative 6 kilogram all over the sum of the two masses, 7.302 times 10 raised to the negative 26 kilogram. So when you do our math, we get the value of the reduced mass of the silicon monoxide molecule, n sub r equal to 1.690 times 10 raised to the negative 26 kilogram, also rounded to 4 significant figures. Finally, in part C, what is the distance between the silicon and oxygen nuclei? So, from equation number 4, right, where the moment of inertia, capital I, is equal to the product of the rest mass, m sub r, and the square of r sub naught. Okay, r sub naught is our target variable. So when we isolate r sub naught, we get r sub naught equal to the square root of capital I, or the moment of inertia, divided by the rest mass m sub r. That is, the value of r sub naught equals the square root of 3.852 times 10 raised to the negative 46 kilogram meter squared. That's the value of capital I, divided by 1.690 times 10 raised to the negative 26 kilogram, which is the value of the rest mass. So, once again, when we do our math, we get the value of r sub naught equal to 1.510 times 10 raised to the negative 10 meters, which of course can be simplified and expressed in nanometers, right? That is, the value of r sub naught is equal to 0.1510 nanometers. So this is the distance between the silicon and oxygen nuclei. Before we end, let us emphasize the key concept we applied in this problem. Because angular momentum is quantized, meaning the quantum number small letter L, the rotational kinetic energy of a diatomic molecule is quantized as well. This energy is proportional to the rotational level small letter L, and is inversely proportional to the moment of inertia of the molecule for an axis through molecule's center of mass. Transitions between rotational states that involve photon emission or absorption are allowed only if small letter L or the angular quantum number changes by 1. So on this note, may I say mabuhay till the next episode. MashaAllah. Thank you very much for your indulgence. Please don't forget to subscribe to my YouTube channel. Alhamdulillah.